So we're going to look at section 3.2, moving into more of a generalized polynomial function. And if you remember, we've talked about polynomial expressions before, and it just basically had a meaning of many terms. And that's exactly what a polynomial function is too. It passes the vertical line test. The function itself has many terms. There are two conditions that we have to be sure that we meet. One of those conditions is the coefficients of each term of the polynomial needs to be real numbers. And another condition is that all of the exponents must be whole numbers. Basically, that means that you cannot have negative exponents and you can't have fraction exponents. So in the box there, it talks about the definition of a polynomial function. It looks pretty wicked. You can tell it has many terms. The fact that it has like subscripts for all of the A's, those are the leading coefficients for each, well, actually they're the coefficients for each term. The one that's going to pretty much play the big role for us is going to be this one right here. This is called the leading coefficient for the polynomial. The other thing that's really important here is to recognize that when you have a polynomial function that's written out term by term by term, the leading term is that one that has the highest exponent. And so we can call this a polynomial function of a certain degree, whatever the highest degree is on that term. So first thing we've got to be able to do is tell whether or not we understand what a function looks like that's polynomial and one that's not polynomial. You'll see here for the first three examples of polynomial functions, they all meet the criteria. You'll notice that if we look at the coefficients, all the coefficients are real numbers. And if you look at all of the powers here, you'll see that all of our powers or exponents are definitely whole numbers. Same thing with the next one. This just happens to have a special name to it. This is called the quadratic function. And the last one here is also a function. It just happens to be the linear function. Those are special cases of the polynomial function. So this first one is just a real generalized polynomial function. Just for practice here, we would say that the degree of this polynomial, the highest degree that you see there, is a 5. For any quadratic, the degree of the poly is going to be 2. And if you look at the linear function, any function that is linear, the degree of the poly will be 1. So those three are polynomial functions. If you look at the next example, it's headed with non-polynomial function. So here they're telling us that we do not have a polynomial function. So what we want to be able to do is recognize why it's not a polynomial function. And this one, there's two reasons. You'll notice that the first term right here has the square root of an x. And what they told us was that every variable has to have a whole number power. We've studied these before. This is really x to the 1/2 power, where the exponent was a 1 inside and the index is assumed to be a 2. So right there, just because of that one term, this is not a polynomial function. But there is another term, if we look at it, and it's right here. When you look at the -3/x term, this has another way to write it. Since the denominator has x to the +1, this ends up being x to the -1, when we rewrite him. And so since our power is negative now, this is another reason why this function is not polynomial. We've been analyzing graphs lately, and some of the characteristics that the polynomial function has are things that you kind of want to remember as best as you can. It'll help you if you do. If you can determine if you have a polynomial function, then your domain is always all real numbers or from negative infinity to positive infinity. Another thing about our polynomial function is the fact that the graph of a polynomial function is what they call smooth and continuous. So down below there, you'll see that we have 4 examples for you. The first one is definitely polynomial. You can tell it's smooth and continuous. The second one is not. It has a sharp point. That's actually the absolute value graph. The third one is not continuous because you can see that it's broken into 2 pieces. That function actually is the rational function. And the last one here is what we call not continuous, because you can see where there's a hole in the graph. We haven't studied those, and the graphs also break. Let me clean this up, and we can take a look at what we refer to as the end behavior of a polynomial function. Here what we're talking about is looking at the actual graph and determining what we call the arms or branches are going to do. It's pretty neat to be able to read an equation without a graphing calculator and tell whether or not the branches of the arm or the arms are going to go up or down, or if they're going to go the same direction or opposite directions, just by looking at the polynomial function itself. And if we do that, we use something called the leading term test. And this is to figure out what the behavior of the graph is going to look like from the left end of the graph and the right end of the graph. We really don't care too much, nor do we know the mathematics to tell what's going to happen in between the right arm and left arm, but we definitely can tell what's going to happen to the arms in the end. The leading term test basically says that when you have a polynomial written term by term by term, the behavior of the graph is going to be determined by the leading term. So this guy right here, because the polynomial is written out by terms, this is what we call the leading term. The leading term, its A value, is going to describe to us what happens with the right arm or right branch of the graph. What they tell us is that if A is bigger than 0, then the right arm is going to go up. If for some reason your leading term is negative, then again, back to the right arm. The right arm is going to go down. So where you and I before, when we were talking about transformations, if the beginning of the function ever had a negative, we said that it would flip over the x-axis, for example. Now what it's doing for a polynomial is describing what happens to the right arm. Now, the other thing that the leading term has, you'll notice in there, is the variable x, and it's raised to the power of n. Well, we just met what n is also called. N is called the degree of the polynomial. The degree of the polynomial. And what they tell us is that if you and I find that the value of n in the leading term is odd, if n is odd, then the arms of the graph will go in opposite directions. So for example, if the right arm were to go up, then the other arm, the left arm, would have to go down. There's an easy way to remember this. If n is odd, that starts with an O, then the arms will go in opposite, that's an O, directions, okay? What they also tell us is, well, if it's not an odd number, since n has to be a whole number, if n is even, then this what this tells us is both arms go the same direction. Now, again, no one's going to take your calculator away from you, so you can always go and graph these functions to double check. But what the graphing calculator won't tell you is why. Okay, so if you look at the 4 pictures that we have up here, the 4 graphs, you'll notice that on both ends of the graph, you have like a darker arrow, and then in between there, it's like a little dotted blue line. Basically, the dotted blue line is I won't say it's a guess, but it's we think the graph could do this, okay? Where the black arrows are, we know that the graph is going to go up, or we know it's going to go down, or one of each, okay? When we start placing the A components with the N components, you get 4 different cases. Here's one of the cases. Let's suppose that N is even, okay? So we saw down here, it said, well, when I wrote it, I didn't write N, did I? Let me come back in here. If N is even, then both arms go in the same direction. All right, so we know that the arms are going to go in the same direction because of N is even. So I'm going to just write the word same right here. The reason why the first picture has arrows headed up is because the leading coefficient was a positive number. The reason why the arms here are both going down is because the N was even, which meant they went the same direction. But now that the leader is negative, that means that the graph must go down. It changes when we get N is odd here. And when we find out that N is odd, we know that the graphs are going to go into the arms of the graph. So for example, if you and I have an odd instead. Okay, so let's take a look right here at the examples that they gave us, and we can tell whether or not the graph's going to go same arms or opposite arms, and we can also tell if the right arm's going to go up or down. Remember, you're concentrating on just the part that we need for end behavior. End behavior. And so what we want to look at then in this first term, we want to look at negative 4x to the fifth. This is what's going to tell us about the end behavior. Here, we're finding out that a is negative 4. So that's less than 0. And we also see here that n is equal to 5. And that's an odd number. So now we're going to figure out what happens then. Remember, A tells you all about your right arm, So if the right arm is less than 0, that means the right arm of the graph goes down. With n being 5, which is an odd number, this forces then the left arm up. They have to be in opposite directions if the power is odd. If you keep going through the examples, you'll see that they're very similar to each other. In B here, we find out that our leading term is a decimal value. Basically what we're looking at is that term positive or negative? In our case here, our A is 0.3. That is a positive number. So this tells us that right arm goes up. When we look at the power of that leading term, his power was a 4. This is an even number. What that implies to us is that both arms go the same direction. So that would imply then that the left arm must also go up. They both have to go the same direction if your degree of your polynomial is even. Now these next two examples, you'll notice, are a little bit different because they're not written out the same way as example A and B. They're already in what we call factored form. Okay, they're in factored form. And if they're already in factored form like this, basically they're hiding some information from us. Earlier, whenever we had, let's look at A. We'll change colors here real quick. And if I go to example A, you'll notice that we had one term plus another term plus another term. If you look at example C, that's not what this says. This says we've got a factor times another factor times another factor. So basically they left us here without multiplying everything out. Don't panic, we do not have to multiply it all out either. But what we do have to determine is if you and I were going to take a look at the value of A, I don't really care what the value is, but I do care if it's going to be positive or negative. And so you can come in here and look at all the numbers that would end up being multiplied together to build that front term. Basically, it's the front of each one of your factors. So if I take 1/4, that's a positive number. So I know I'm going to have a positive number. He'll be timesed up against, if you look at the next factor, he has a 2. That's a positive. So I know I'm going to multiply by another positive. When you cube a positive, it's still positive, so I don't have to worry about it. And then the last factor here has an understood 1 in front of that x, which happens to be another positive multiplier. So I can pretty much tell that A is going to be bigger than 0. All the numbers that we were multiplying out in the front of each one of their factors are positive, so it's bigger than 0. And that tells me right then, we know that the right arm is going to go up. Now to figure out what's going to happen with n, once again, they did not share that information with us. N is the number of degrees. And so what we have to do here, since it's in factored form, we have to look at all of the powers that the x factors would have. So for example, my first term here is really 1/4 x to the first. So I know I have 1 power. I'm going to add that then. If I look at the second term, or the second factor rather, I have 2x to the 1 again, but this happens to then be cubed. So 1 is going to happen, 2x to the first is going to happen 3 times. So that would be 3 powers from that factor. And then when I look at my last factor, this is x to the 1 also in there. But notice he's going to ask me to do that twice. So I'm going to add 2 to it. And that gives me n is equal to 6. Since 6 is an even number, that implies that both arms are doing the same thing. And so if the right arm is going up, the left arm is going up too. If you look at the last example there, you'll see that sure enough, we start off with a negative 6/7 times a 1 in front of the x times another group of 1 in front of the x times another group of, there's a 3 in front of the x. So I have a negative times a positive times a positive times a positive. In this case then, my a value is going to end up being negative. That's going to be less than 0. I know now that my right arm is going to go down. If I look to see what my n value is going to be, I have to go to each one of my factors, look for their variable, and determine what the power would be. What you'll notice here is when things are factored, if it's going to happen more than one time, we write it with an exponent on it. So like, for example, this is an x to the first power, but it's going to happen 4 times. So 1 times 4 is 4. Again, x to the 1 in the second factor here, 1 times 2 is 2. And then the last factor, this term is 3x to the 1. It's not going to happen multiple times, so I'm just going to add 1 to it. Notice I didn't speak about negative 6/7. And the reason why negative 6/7 doesn't help us is because there's no variable with it. So if I were to add these together, I do get 7. 7 is an odd number. And so odd means opposite. So if the right arm is going down, left arm is going to go up. Okay. Now, another feature of a polynomial function is talking about what they call the zeros of the function. And the zeros of the function, we'll see this right here, happen whenever you place the function equal to 0 and you solve for it. We've done this before. This is the same technique we use for finding x-intercepts. So it's not surprising that the x-intercepts are also considered to be zeros. We actually call them the real zeros because they're on the number line. You can have imaginary zeros, and we'll see that a little bit later on. Another thing that we're interested in that we kind of looked at without you knowing it is a 0 can have multiplicity, which means a 0 can happen more than one time. It can happen twice. It can happen 3 times. What we know is that if a 0 has an odd multiplicity, so if you find out that one of your answers to the equation equal to 0 occurs more than one time, then the graph does what we call a crossing. Call it a cross point. This graph will cross the x-axis at that value. And then if for some reason your 0 has an even multiplicity, then the graph is going to touch the x-axis, and it's called a touch point. So sometimes you'll see graphs that will wiggle, and sometimes they'll wiggle and they'll touch the x-axis and then go right back where they came from. And that's what we mean by a touch point. All right. Probably one of our favorite examples might be for this, for a touch point, might be when a parabola comes down and touches the x-axis right there. That's called a touch point. If you and I have a cross point, we're talking about whatever graph we're using at that time. I'm just choosing the quadratic, it's easier to draw. These are called crossings. So this is a cross point. Both of these are. This is a touch point. So let's take a look at what we can do with the first example then. It says find the zeros. And when you read that, again, remember, a lot of times we're having trouble with not understanding what we're asking you for. And so what we need to practice on is when someone says, I need you to go find the zeros, then you need to realize we just told you to set f of x is equal to 0. That's what we told you to do. So if we come up here to this problem and we say 4x to the third minus 4x squared minus 25x plus 25 is equal to 0. Now we have to rely on what we know about a polynomial equal to 0. There's 4 terms. If there's 4 terms, we should pair them. First 2 terms together, last 2 terms together, and hope that it factors by grouping. So in this first group, they have a GCF of 4x to the second, leaving me with a x minus 1. The third term will give us his operator. And now in the 2 terms, they have a 25 GCF. Be careful, this gives us an x minus 1 is equal to 0. One last step and we'll have it totally factored. X minus 1 seems to be the common factor for those two. And we have a 4x squared minus 25 is equal to 0. So when you're solving a polynomial, one of the first things that you're going to try is, will it factor? The reason why we can't go back and use the quadratic formula here is this is not a quadratic function. Its high power is 3. So you have to, well, we hope that it'll factor for us. Now, am I looking through here at these factors? I know that x minus 1 is finished because there's no GCF and there's no way to factor that further. But I'm looking here at 4x squared and 25. They're both perfect squares with a minus in between them. I think I've got a good shot at factoring those a little bit further. How about 2x minus 5 and 2x plus 5? When we were solving a quadratic equation with factoring, we relied on the fact that we had the 0 factor theorem, which allows us to come in here, divide this up into factors, and set each one equal to 0. Solve. If I add 5 rather and divide by 2, this will be positive 5 over 2. And then this last one, if I subtract 5 and divide by 2, I'll get the negative of 5 halves. One of the things that gets to be a little bit confusing in mathematics is how you write the answers will tell people if you're looking at a point, if you're looking at a value, if you're looking at something specific. And so the way that we write out zeros, we just list the numbers. So like our zeros are 1, -5/2, and +5/2. Now, when we go to graph later on, we'll identify those zeros. Since they're real numbers, we'll actually identify them as x-intercepts. And so when we get ready to go to the graph and we want to go and graph things that we can find, our x-intercepts are actually 1, 0, -5/2, 0, and +5/2, 0. Those are our 3 x-intercepts. We would write them that way if we wanted to go graph. Okay, so the answers here are 1, -5/2, and +5/2. The next example asks us to do the same thing. It says find the zeros. So once again, as long as we understand what it's asking us to do, then we'll know how to set this up. So you want to know what the zeros are, that means set the function to 0. When we do this one, we have a cubic again, which means you can't use the quadratic formula to solve this one because it's not a quadratic. If you look at the 3 terms that they gave us on the left-hand side here, they all have an x-GCF in common. So I'll factor that out. I can also see in here, I've got a perfect square leading term. I've got a perfect square in the back of the polynomial. So I think we have a shot at factoring this further. X plus 5 and x plus 5. We'll go back now and split where our factors are since it's equal to 0. And now we can go solve. This first one, when I set it equal to 0, that is one of our zeros already. When I set the second factor equal to 0, this gives me -5. And when I set the next factor equal to 0, I get that exact same answer. This is what I was telling you about earlier about this multiplicity type thing. Multiplicity just tells you the number of times a 0 actually occurs. And so right here, if someone was asking us what happened, that's the same 0. What we'll tell people is when we go to list our zeros, we'll tell them we had a 0 that was 0, and we had another one that was -5. Now, the way we need to explain to people that because our high power was a 3 in the equation, we were expecting 3 zeros. That's what your degree will do for you. And so what we'll say -5, and this has a multiplicity. Don't think I have enough room right there. Come underneath there for you. -5, I'll put with multiplicity of 2. And what that tells everybody is that when we were solving this, yes, we got 0 as an answer. That's where the graph is either going to cross or touch. And at -5, -5 actually occurred twice in our work. So we can write this as -5 is the unique 0, but it will have a count of 2. One of the things that we use multiplicity for is to help guide us in our graphing. And what you can see in this example now, we can already predict what's going to happen. I know at 0, since this only happened one time, I know that my graph is going to cross. It's going to have what they call a cross point. Because how many times did 0 actually become one of our zeros for the function? This only occurs once. So since this only happens
one time, that's how come we get a cross point. Cross points come from odd multiplicities. Odd multiplicities. Here, -5, it happened twice. And so at -5, when we look at that value on the graph, not a big surprise. This is going to be what they call a touch point. And that's because we had a multiplicity that was even. The multiplicity of -5 was even. And so our graph would touch there. One thing you can do is always graph this in your calculator and look at the picture to see about the touch and the cross. Here's another example. It asks us to find the zeros once again. And with all these different types of examples, what we're trying to do is expose you to some of the things that can possibly happen. So once again, the mathematics is the same. We'll still come in here and put x to the 4th minus 2x squared. That's equal to 0. Both terms have a GCF of x squared. And now this x squared minus 2 factor that you see here won't factor any further. So I have to go with the 0 factor theorem that says set each one of your factors in equal to 0. So there's x squared is equal to 0 and x squared minus 2 is equal to 0. In order for us to solve something that has an x squared in it, since there's no more x's, it's isolated, and we'll come in here and take the root, the square root of both sides. Now I'm going to write something that's going to look a little weird, but don't forget that anytime you take the square root on both sides of the equation, you get 2 answers that form. The reason why I said this is kind of weird is because 0 doesn't have a sign. And so when we come up with his value, when we take his square root, we find out that x is equal to 0. Now, there's not a positive 0 and a negative 0. However, we do need to realize that because the power on this factor was squared, it was a 2. This means that the 0 here has multiplicity of 2. What that means is that if you go and graph this function, it's going to go to the number 0 on the x-axis, and it's going to touch and come right back in the same direction it started. So at x is equal to 0, we're going to end up with a touch point. For the other factor, let me bring that up here. X squared minus 2 is equal to 0. Since it won't factor down any further, I can isolate the x squared by adding 2 to both sides. And now I can use the same technique. Take the square root of both sides. Remember that you're going to get 2 answers when you take the square root. And so when we take the square root of x squared, we get x. 2 is not a perfect square, nor does it have a factor, so we're going to have the square root of 2 as one of our zeros, and negative square root of 2 is one of our zeros. The power on this function was 2, and I did get 2 different answers here. So when I'm writing down the answer to the problem, what are your zeros? I have the number 0 with multiplicity 2, which I found out is going to be a touch point. I also found out that I'm going to have the square root of 2. When something only happens once, you can classify that as multiplicity of 1 if you'd like to. 1 is an odd number, and so that's what tells me my graph will cross at this point. And then the negative square root of 2 does the same thing. If you'll go back and count up your multiplicities, you'll notice that 2 plus 1 plus 1, that's 4. And that should match the high power of your polynomial if it's written term by term. And sure enough, it does. Another example, and the reason why this one is unique, if you look at how it's been written, this is not written out term by term, it's written out in factors. This is written out in factors. Well, a lot of times that's good news for us, because if the instruction says find the zeros, then that'll be one part we don't have to go and figure out by ourselves. So find the zeros, it's already factored. And since this is already factored, we can start our procedure. I'm just going to write a note here. Poly already factored. Since we're finding the zeros, what that means is that we would have each one of these factors split away from each other like we've been doing. So this time we didn't have to factor it. It was given to us in factor form. And now we can go back and solve. This x squared would equal to 0. If you take the square root of both sides, you do get 0. I'm going to remind myself right here, the multiplicity is 2. X minus 2 cubed. You can think of this in a couple different ways. On your filled out notes, I kind of did it with the root involved here. If you think of it this way, this just means x minus 2 times x minus 2 times x minus 2. So if I were just to set one of those multiple factors equal to 0, I'll find out that x is equal to 2. If I look back to see how many times this would have happened, the multiplicity is 3. Remember, exponents are just shorthand notation that tell you take this base and times it by itself this many times. The last one here, I'll do the same thing. I'll use x plus 4 as the factor. Solve it, get x is equal to negative 4. Look back up to the problem. He says he's going to happen 7 times. So my multiplicity is 7. What will happen at 0 if your multiplicity is 2? You'll have a touch point. At 2, where the multiplicity is odd, the number 3, you'll have a crossing. So this is a cross point. And when x is negative 4, the multiplicity was 7. Since 7 is odd, it gives us a cross point. Your zeros are the number 0. He has a multiplicity of 2. Another one is the number 2. He has a multiplicity of 3. And then their last one is negative 4 with a multiplicity of 7. What this tells me is that if I went to the pain and suffering of multiplying each one of these factors in the original problem, all of them together, like it's insinuating, you and I would have a power, a degree of, let's see, 7 plus 3 is 10 plus 2 is 12. Our first term would be whatever number times x to the 12th. X to the 12th. The next example that you see here gives us kind of like a step-by-step procedure of how to actually go and now graph these on graph paper the best we can. These are the different characteristics that I'll want to see on your graph when you go to, and this is what's key here, you will be sketching a graph. There will be some points that you can plot, but for the most part, the only thing that you'll be able to identify for me, you will plot the y-intercept. You will plot the x-intercepts. Remember, x-intercepts are zeros also. From this, you'll also be able to tell from any multiplicities if they're cross points or touch points. And then another thing that's kind of helpful sometimes. It really doesn't play that much of a role uniquely, but it is a helpful hint, is determining how many times the graph should turn. Notice what you have to know in order to do that. You have to know the high degree. So whatever your Poly's degree is, minus 1. And so if your high degree is 4, if you take 1 away from it, that would be 3, which means you have the possibility of having 3 turns in your graph. Probably one of the best examples that you and I have already run across would be, what if you had the function x squared? Here our degree is 2. And so if I ask you the number of turning points, you would take your degree, which is 2, and subtract 1 from it. So you should have at most 1 turning point. The reason I picked this one is because this is the quadratic. And if you think about drawing a parabola, how many times does it turn and change direction? That's what we mean by turn. So here he was decreasing. Right here we call this the vertex. And then he changed to an increasing graph. So sure enough, he has 1 turning point. That's an easy one to kind of keep in your memory. So let's look at the example here that asks us to go through the actual graph itself. On the notes that I've given you in filled in notes in Canvas under module 3 test material, you'll find that I've done both of these examples for time purposes and the length of this video. Let's take a look at the top one here. One of the very first things that you'll want to identify, of course, will be behavior. We want to make sure that we understand if the graph's arms are going to go up or down. Are they going to go the same, or are they going to go different? And so if you remember from the very first thing today, we said that A is in control of whether or not your right arm goes up or down. In our case, our A value, which is the leading coefficient, is -1. This is less than 0. That automatically forces the right arm down. The second part of behavior will allow us to figure out what happens with the left arm. We need the n value, which is the degree of the polynomial, or the exponent in the leading term. This is the number 3. The number 3 is an odd number, so that implies that your arms will go opposite of each other. So that's going to force the left arm to go up. So we already have an idea of how the arms are going to look. What we need to determine now is, are there any points of interest to us? And one of those points of interest will definitely be the x-axis. Where do we cross the x-axis, or do we touch the x-axis? So we'll definitely be looking for x-intercepts. I'm going to put this plural out here to indicate there may be more than one. A good indicator for us is that if you know what your n value is, this is a real good indicator. Oops. This is a real good indicator right here to let us know how many x-intercepts we should be looking for. Okay. There'll be the fundamental theorem of algebra will be coming up pretty soon, and so I'll once we get there, I'll explain that information to you. For the x-intercepts, then we've always been told to let y equal to 0. This is the same thing as if we were solving for zeros. So it gives me a little equation here. I'm going to go through here and multiply through by -1 so that I can have a positive leading term. Now, since it's not quadratic, I have to use my factoring techniques. They both have a GCF of x. And I did get lucky here because x squared minus 4 factors into x plus 2x minus 2. And now I can find my x-intercepts. Split where you see multiplication happening. X is 0. If we set x plus 2 to 0, we find out that x is -2. And then if you set x minus 2 to 0, you find out that x is 2. So since we're actually plotting and they ask for x-intercepts, we will write these as points. Those are our x-intercepts there. Another one that'll help us when we go to the graph will be, where does it cross the y-axis? There's something unique about this graph here, but let's go ahead and show you what we would do. To find the y-intercept, you're going to let the x equal to 0. And so when we go back to the problem here, this would be -0 cubed plus 4 times 0. And if you do the arithmetic, that's equal to 0. And what that indicates to us is 0, 0 is the y-intercept. Now, I kind of already knew that, because if the x-intercept is 0, 0, that forces the y-intercept to be 0, 0. That's the only one that works that way. So now I have 4 points now that I can actually go and graph. Something that'll help me on this graph. And like I said, in my notes, I did go ahead and do the last example too for you. But for time purposes, let me take this out of here right now. And let's go back and revisit what happened at these x-intercepts. At 0, 0, this came from a factor that was to the first power. So this is going to have multiplicity of 1. So that means it's going to cross at x is equal to 0. -2 came from also a factor raised to the power of 1. So he also has multiplicity of 1. So we're going to cross at x is equal to -2. And then this last one here also came from a factor that had a power of 1. And so we'll cross at x is equal to +2. So when we start putting this graph together, one of the things that we can do, remember this is a sketch, we can go in there and tell it that we know where the y-intercept is going to be, right there. We can also go in there and tell it we know where the x-intercept will be. It happens to be another just 0, 0. I'll just put it on top of it. But there's 2 over. So there's 1 at 2. And there's 2 over this way, which is -2. If we use some of the guides that we've analyzed up here, we said that the behavior, the right arm has to go down. So I know that below the rightmost point, my arm will have to go down. If I look at what happens to the left arm has to go up. So the leftmost point has our up arm. How will I know how to like wiggle through these points? You can only cross the x-axis at these 3 different values that have points on them. And that's why it was so important for us to know, should I cross or should I touch? And at each one of these, the graph actually crosses the x-axis. That means you go through it. So what I know, and I'm going to change colors so that you can see the part I'm not 100% sure about. I do know that I'm going to cross through -2. Now, what I don't know is I don't know how far down to go. I have no idea. But I do know that on my way back, I've got to cross through 0 and then turn somewhere, which I don't know where, and cross through 2. So in our class of 24 people, I could relatively have 24 different looking graphs. And what I mean by that is someone might come in here and think, well, I think that this graph is going to go through here, but buckle right there, and maybe buckle there. So until you get into calculus, you can't really tell where these relative maximums and minimums are going to be. So we're eyeballing this. If you get it exactly like the graphing calculator, that just means you copied what the calculator told you. So what we're doing is we're just analyzing the graph at this point. All right, I hope this helps you get through the section about polynomial functions, and I will talk to you later.